for me that there is no any ghost or unphysical state. I can see that the energy becomes complex if I pass the border to the left. If my momentum becomes lower than that, so below this range, so the energy becomes complex number. So from this theorem needs some proof, but I jumped from the proof. So the corollary is that no any physical state with the momentum less than that. And but you needed a lemma. So for the lemma is that you need to consider the dispersion relation for the momentum just slightly to the left. So just think about this is the border momentum, and just to take it a small yeah, so deviation, exactly, deviation from that. And then after that, you will see that you are not able to solve this equation for the real number. So the energy becomes the complex numbers. So I know that in electromagnetics we have a case that even the refraction index or something becomes the complex even. But I don't know any case about that because energy negative even have a problem. So just imagine the complex energy will be dramatic. So so this is I want to jump from that, but this is the proof of this theorem. So you can find it in the, if somebody wants interest, you can read it in archive. So now I just few minutes I want to talk about the Riemann hypothesis and the relation with our calculations. Your Riemann hypothesis is a 160 years old prize, and the problem is very simple. You have a Riemann zeta function, the function which appear in the Bose-Einstein condensations, and we have a new version of that here called Lerch function, and it's about the poles of this function, where are located the solution for the roots of this zeta function. So zeta function has the poles over the negative integer numbers, and if you make the analytic constitutions to the right hand side of the plane, Riemann write a paragraph in one of his during a conference, and he said that okay, if you make the complex extension of my functions, I can prove for you easily that the roots they will be existed over this they call it later critical state. All the roots of the zeta functions are negative integer, or they are located under this state. The real part of the solutions for the zeta function equal to the zero equation will be located here. So, so it means that you need a mechanism of the Bose-Einstein or something that the argument of the Bose-Einstein function or the argument of the Lerch function could be complex number. So how you can generate the complex number inside the density of the state functions? So again we play by the math. So if you choose the density of the state like that, like the form which we propose it here, you can use either cosinus or the sinus. So that gives you again the weight to the energy state. So, and if you forget about that and that, if you restrict the A to the 3/2, 1.5, so you get the normal non-relativistic Bose-Einstein condensation. So that was the atypical Bose-Einstein condensation. And if you added this part, I want to tell you that by this part you can make the complex argument to your Lerch function, and you can make the complex argument to your zeta function. So I repeated the calculation for this new type of the density of the state. So finally you will see that the Riemann hypothesis becomes softer. So it becomes, it translated to the problem of finding the specific value of the higher temperature, critical temperatures. So why I say that? Because if you repeat the same calculation, you will see that the critical temperature comes like that now. And here, instead of the normal zeta function, you will have the real part of the Lerch function. And finally, we have the complex argument. So the discussion was that the Riemann want to prove that the roots of this function existed over A is equal 1 over 2. A is half.
What is the physical meaning of this first argument, A plus 5? I forgot.
This one?
Yes, this one. What was the... Yes.
The motivation.
What was the physical parameter for that? That was energy?
Yes. That was the density of the state. So we modified the density of the state by introducing two extra parameters here, actually, A and the B. And if you introduce it A and the B, you can make the Lerch function complex, this. And when you make the Lerch function complex at the criticality, it gives you the zeta function as a complex argument.
You are using the hypothesis of the Riemann for the right part.
Yes, I wanted to generate the zeta function with the complex argument from the Bose-Einstein condensation, and we generated those actually. With this density of the state, you can find that. So I will finish just a few minutes. So and finally. Honestly, I didn't get the zeta functions. I get the real part of the zeta function, unfortunately. So it needed to think that how we can get exactly because actually zeta function appear as the critical temperature or something like that. So you needed to use the absolute value of the zeta function or real part of that or imaginary part of that. You cannot have the full version of the zeta function in the complex argument. So this is the equation, and from this equation you will get very interesting fact, is that finding the roots of the real part of the zeta function reduced to the problem of taking the limit of the expression when h bar tends to the 0. No? And this is called the classical limit. So if you can find any evidence about the classical regime of the Bose-Einstein condensation, you can get some information about the roots of the zeta function, at least the roots of the real part of the zeta functions. So this is a bit mathematics. So I was trying to see that is it any information about the real part of the argument of the real zeta function or not? And in the literature, there are some discussion that show that the supremum of the A can be 1.19. So I mean that you have estimation about the A, but still, we cannot prove that. It becomes a little softer, but it still is unsolved. So we cannot prove that exactly that when A is half, so the right-hand side will be 0 definitely, even for the real part of that. If you can find some kind of the classical regime for the Bose-Einstein condensation, the classical regime can help you to find the roots of the zeta function. So the idea was a little bit more abstract. So I had a difficulty there. So this is the original Riemann hypothesis, and this is the lemma which you needed to prove actually. We needed to looking for the phase of the matter corresponding to the density of the state, which I proposed it with the A 1 over half in the classical limits. And the last part of my talk is I try to quickly pass from that. So thanks to these functions, we are able to define two operators, the ladder operator, creation and annihilation operators. And they are not actually non-self-adjoint linear operator, but they make some kind of the Hilbert space. So this is the checking that they are not form a simple Hilbert space. So they don't respect the hermiticity actually. So, and exactly following the same strategy we use in quantum mechanics, using these two operators, you can define a number of operators, and this part is the work of the Lagrangists, so these big, great mathematicians. So he did this calculation. He was not able to interpret that. So I just think that maybe we can interpret that like the simple harmonic oscillator. You see that they are very similar to the creation operator algebra in the simple harmonic oscillator, but not exactly that, but very similar. But the last equations is like the number operator over the wave function gives you the number of the particle over the wave function. And these equations have a little problems. Actually, you see that some kind of the creation and annihilation phenomena happened here, but it seems that the number of the particle is negative or complex number. Huh? But actually, I solved that. So I need to just run from that. So just softly modify the definition of the number operators. You can define a number of the states, number of the particle in each energy state in the equation 38. So this n never gets minus or any other else. Even it never gets complex. If you set even new the complex number, this number always it will be real actually. So for new to the, but there is still problem, and it becomes finite, becomes infinite, diverge at the new limiting tends to the 1. So, and I made it also the formulas for the coherent state. So it's possible to make the coherent state for that, for this system, in the same style which we do in the classical field theory and in the quantum field theory. You can build the coherent state. So this is the coherent state, but the nu is the free parameter. You can choose any number, even the complex numbers. But the problem is that the normalization factor of the coherent state is given like that, and the doubt is that maybe this series doesn't converge. So maybe you have some kind of the coherent state with the infinite number, occupation number, or something like that. So what I'm doing now is, and also later, I used the principle, the variational method, and I estimated the real part of the argument of the zeta function. So just by the simple variational method, by one trivial function, you can get one of the poles of the zeta function. I told you that the poles for the zeta function existed. The trivial poles are the negative integer numbers. So one of the negative integer numbers can be obtained by the variational principle applied to this functional. And this functional involved some trivial function, and it is operation creation function. I think this is a very interesting starting point. May it's possible to generate all the trivial poles of the zeta function using this minimization principle, the Ritz principle. And maybe it's possible also to find the location of the poles of the Riemann zeta function in the right-hand plane, complex plane, and show that they are existed over this string. So, but it depends to choose the trivial functions correctly. So, actually, what I'm doing now is that I'm developing the thermodynamics, and I'm trying to generalize the variational principle to find the all roots of the Riemann zeta function. But this is a very different idea and very different. I removed a lot of detail here, so maybe this talk not very, not looks like very continuous because I deleted some things. So, and the other problem is that if you make all of this field theory, classical field theory, or how you can call it, quantum field theory, any quantum mechanics, what's the problem of convergence? It is possible to have the finite value in your theory or no? And still I'm working on that, and this is the references. So the last reference is my paper actually, this fresh paper from the kitchen just. So February. So the first 5 papers are the groundbreaking works of these mathematicians, so the Jeff, and the other one is the video just about this $1 million. So I didn't get this money, so if I get, I don't know. I think this is...
Share it.
No, of course not. No, it is a joke, but it is just interesting for me because I'm interested to the questions. So it was a joke just to get this prize or something. It's just we are just thinking about something which we enjoy, and that was interesting for me. So thank you very much, and I'm sorry that the talk took a long time. So.
Unfortunately, I could not attend
Yes.
to the whole of the lecture because of my
No, we started by delay, so you came exactly at time.
No, I have a little bit of generic question.
Yes.
I understand that you have been describing non-interacting interacting bosonic systems.
Yes.
But now, if you go beyond that, like say for example, if you go to say Cooper pairs,
Yes.
like the Charles bosons.
Yes.
So do you think that sort of approach, a similar approach can be made to understand the charged bosons like the Cooper pairs?
Actually, that's very important question, but really I don't have the idea. You know, when the interaction enters the systems, or it's very complicated. We need to use the cluster expansion method. And
electrical in
Yeah.
nature, because you know that when you have the electron, I mean, you know that superconductivity solution when the spin up and spin down
Yes.
combines together to the zero spin,
yes.
which is essentially the boson system, but it is charged.
Yes.
So in that case, whether the charged bosonic systems can be somewhat incorporated in your model.
Sure. I think it can, but I don't know how to do that. Really, honestly, I don't know that. That's very interesting.
As a kind of perturbation to the potential.
Yeah,
I don't
that's
think so. I don't think so, because this is a strong interacting system.
Oh.
Perturbation works only when there is sort of good type of interaction. Because this is strongly, say for example, when you have the Cooper pairs, the particle has got 2e of charge. So they are very strongly interacting particles. So I don't think that any perturbation theory can be useful there. One will have to go into non-perturbative sort of treatment there.
Yeah.
Entire quantum system. If the perturbation will be weak, then definitely you can expand it and take
But you also
something
can
else.
ask if the properties are in like a fluid or somehow, so that the interaction will be weakened.
I don't think so, because when you think, because when you get into the say superconductivity, then these are only
They are very
the
close to each other.
they do they strongly interact with each other.
Dawood, I have another
Yes.
question. In the very first part where you used your density function,
density of state.
I saw the factor C. Can you show how did it enter the density function and how you make it up?
Yeah. So yeah.
The
Yeah,
very first equation.
Yeah, after if we introduce the pair of the creation and annihilation operators, you will see that fortunately we needed this C to define a pair of the operators. Yeah.
In the very first one.
Yeah, in the very first one we have the C. Yeah.
So how do you justify adding it to the density of states? What is the physical motive? You say
At beginning, no any physical reason, really. Honestly, I had no idea about at beginning. I just was looking to try to regenerate the generalized zeta function. I call it Lerch function. So I was playing with the argument to see that how to include this argument. For example, it was an idea to introduce that like the interaction or something. Still, this idea is. So it was just by hand. I just.
Someone would say that the original density function already explains the
Yeah.
system well.
Okay.
So how would you justify keeping?
But this is an atypical Bose-Einstein. I call it this atypical, yeah. Because the dispersion relation also comes different from the normal one. So, because the range of the critical temperature will be different. So if in future, if they find some new range of the criticality for this Bose-Einstein condensation matter, may it's possible to make motivation